Hello all, season's greeting to all of you. Thank you for joining us in this webinar. I'm Kishan Joshi, the chair of PEL's San Francisco Bay Area chapter, and it gives me great pleasure to continue bringing more power to 2022 as we get closer to the end of the year. Here's a little bit about our chapter. Recently, we were the recipients of the 2022 Santa Clara Valley Outstanding Chapter and the 2022 Region 6 Outstanding Chapter Awards, along with the 2017 PEL's Best Chapter Award. Today's talk is on common mode EMI analysis and mitigation methods in three-phase inverters by our very own XCOM member, Dr. Giovanna Oriti, professor at Naval Postgraduate School. I would like to thank the support from our wonderful IEEE co-sponsors who help us spread the word around and help us in bringing forward these webinars to you. The IAS Education Department and the Santa Clara Valley PES IAS chapter. There's a lot of work that goes on in the background in organizing the events and bringing initiatives to our membership. I would like to thank the support from our excellent team of officers and volunteers. None of this would have been possible without their support. Do not forget to check out our new website for info about the current and past talks. You can also follow us on Twitter at SFBAC_PELS for more updates. We are excited to bringing not only more webinars in 2023, but also bringing back in-person events in the Bay Area going forward. So please be on the lookout for those. If you'd like to be in loop on all the great talks and events happening, then IEEE eGrid is the location to go to, since it delivers all of that info down to your inbox for free twice a month. Be sure to register at the link shown here. Thank you for being here. The PDF slides and the recording of the webinar will be uploaded to the archive section of our website, which you may refer later. Now, a little bit about our speaker today. Giovanna Oriti received the laurea with honors and PhD degrees in electrical engineering from the University of Catania, Italy in 1993 and 97 respectively. She was a research intern at the University of Wisconsin-Madison for 2 years, then worked in the industry for 10 years. In April 2008, she joined the faculty of the Electrical and Computer Engineering Department of the Naval Postgraduate School, where she is now a tenured professor. Her research interests include electromagnetic interference in power converters, power electronics for energy management, shipboard electrical power, microgrids, and renewable energy interface. Without further ado, I would like to hand over the stage to Giovanna.
Thank you, Kishan. I'm going to share the screen. Hello, everybody, and thank you, Kishan, for the kind introduction. Today, I'm going to talk about common mode EMI analysis and mitigation methods in three-phase inverters. So this is the overview of my presentation. First, I'll talk about what is conducted EMI in power converter, some definitions. I will focus on common mode EMI and modeling. Then I will talk about methods to eliminate common mode voltage in three-phase inverters in both grid forming and grid following inverters, as well as applications such as motor drives. And then I'll conclude my presentation and talking about future work and some references. So let's start with some references, some definitions first. Definitions, we have to start, of course, with what EMI is. Electromagnetic interference is a degradation of the performance of an equipment, transmission channel, or system caused by an electromagnetic disturbance. And it can be conducted or radiated. And conducted is current that couples into other parts of an electrical system. Radiated is electrical or magnetic field that can potentially couple into nearby circuits. And also, when we talk about EMI, we often talk about EMC as well. Electromagnetic compatibility is the ability of an equipment or system to function satisfactorily in its electromagnetic environment without introducing intolerable electromagnetic disturbances to anything in that environment. And these are definitions from the Senelec Guide 24 from the European Committee for Electrotechnical Standardization. So we want to talk about camo mode specifically in power converters. And but first, let's understand what it means. In this picture here, I show a typical power electronic system that could be a motor drive, where there is a power source, there is an inverter, in this case a DC to AC, a three-phase inverter, and there is a load, which can be a motor or others. We have to notice that there are differential mode and camo mode currents. So the differential mode currents flow from a return to their source of origin, but they can also contain high frequency components that are not desirable. And we can see here, for example, on the DC side and on the AC side as examples. But they also have camo mode currents, which are usually not flowing at low frequencies, but they do flow when there is high frequency components, such as those produced by switching power converters, like an inverter for a motor drive. So these currents go all in the same direction, as you can see in this picture here. And they, if there is a path to ground, that they will flow through ground, and that's not something that we desire. These impedances I'm drawing here in this picture are usually parasitic capacitances. And there is parasitic capacitance between the motor winding and the chassis. And since the chassis is grounded, then the capacitance between the winding and the chassis will appear to ground, providing a path for the camo mode currents to flow if the frequency is high enough. So these will not circulate at low frequency, such as 60 Hertz or 100 Hertz, but they will circulate at the switching frequency of the inverter. So, and this, of course, because the impedance of a capacitor is inversely proportional to the frequency, right? So this will become more and more like a short circuit as the frequency goes up. So going to the next one. So these camo mode currents can trip ground fault relays, damage motor bearings, and produce radiated emission. So they're highly undesirable, and they need to be stopped from flowing. How do they? They're generated by camo mode voltage in the switching converter. So if we eliminate the camo mode voltage, then we can reduce the camo mode currents flowing in the system. Here I'm showing an example of typical three-phase two-level inverter with a DC bus and a LC filter at the output. And here I have the waveform, typical waveform that most of you recognize, right, for pulse width modulation for each of the three phases. So phase 1, 2, and 3, as shown here in the picture. In addition to the voltages here, we have what is called camo mode voltage, which is the sum of the three voltages divided by 3, and is shown here in this picture. So this is the voltage that drives the current that will be flowing through ground. So there are limits and standards for conducted EMI. So we want to reduce them, and so in the commercial world, for commercial products, there are limits set, for example, by the FCC in United States or by CISP and IEC in Europe. And these are just examples. There are also specific standards for specific applications, such as commercial transportation application, like automotive. And we have the SAE J1113 standard or IEC CISP 25 in Europe, and also aviation, of course, standards. These are all EMI standards meant to limit the production of EMI in a product that is being sold in different countries and for different applications. Then we go to the stricter standards, the military standard 461G, which regulates conducted and radiated EMI for shipboard and aerospace application. These limits are the hardest to meet. Power converters on board of military ships must meet simultaneously the conducted emission limit in military standard 461G, as well as all the other specification in 1399, military standard 1399, which refers to low voltage AC application as examples. So we need to take that in account, not just when we design for EMI. So here I'm just want to show a little bit of this standard that I'm talking about. So Military Standard 1399, Section 300, Part 1 for shipboard application was revised recently in 2018. I'm showing here pieces of Table 2, which is a table that takes the entire page. I'm only showing some pieces to show frequency characteristics and voltage characteristics. The type of power on board ship submarines is divided in type 1, 2, and 3. We are going to focus in this presentation on type 1 power, but of course, same ideas can be applied to the others. So type 1 power is 60 Hertz with voltage that could be 115 or 200 volt RMS or 440. And the standard, in particular, this table shows the limits. So, for example, here on item 8, line-to-line voltage imbalance has to be limited to 3%, and so forth. There are also power quality standards. So, if you scroll down the rest of the table, in the military standard, you'll find also THD and maximum individual harmonics limits, so power quality limits, as well as others. So let's talk about also briefly about military standard 461 specific to EMI, requirements for the control of EMI characteristics of subsystem and equipment. This was revised in 2015. I'm showing here the two charts. On the left is CE, where CE stands for conducted emission 101. For the lower frequency range, ranging from just above 60 Hertz all the way to 10 kilohertz. And then this is audio frequency currents. And C102 instead is conducted emission at the radio frequency from 10 kilohertz to 10 megahertz. These curves can be relaxed depending on the power level of the equipment that's being tested. And for example, here for C101, the dB relaxation is given by 20 log of the fundamental current. For the C102, the relaxation is given by this table and depends on the input voltage. So these are the standards that we are dealing with when we design for EMI. So having to meet these standards, what are the solutions when you have power converters, power electronics equipment that needs to meet these limits and standards? On the left, I have here EMI filters. This is very well known. EMI filters can be passive or active. Passive filters are widely known. There is all kinds of different types, such as camo mode chokes, for example. They're very popular. They're cheaper with respect to the active filter. They don't require control equipment or electronics, but they can be larger in size and heavy. And there is a limit on how many bypass capacitor you can put in on a shipboard, for example. The active are more flexible and, of course, cost and increases in the number of electronic components, potentially reducing the reliability. But more and more, we try to design for electromagnetic compatibility, as I'm showing here on the right-hand side. And these are examples of how we design for EMC. We can balance circuits, for example, or we can reduce a DVDT. Balancing the circuit includes changing the converter topology or finding alternative modulation strategies. Reducing DVDT can be done with new gate drivers or reducing the switching frequency, for example. In this presentation, I will talk about solutions that we have been investigating where we change the topology and we look at alternative modulation strategies. But in order to do design for EMC, it is important that we are able to model the camo mode. That's a key to be able to design for EMC. And I'll talk about modeling first. Next. Before that, background about this research I will present later. So some background information regarding the four-leg inverter. So I showed earlier a three-phase, three-leg inverter, typical two-level converter. But the four-leg inverter is an alternative topology that can be used, especially if you have a four-wire system. In the late 90s, while I was at the University of Wisconsin-Madison with the late, much beloved Professor Lipo, I had the pleasure of working on this for the first time, adding at the fourth leg to cancel common mode. The reference is this paper from 1999. We did this and we were able to do it with soft switching converters at the time that were investigated at the University of Wisconsin-Madison, and pulse density modulation was used for soft switching inverters at the time. We were using the resonant DC link, for example. But now we're thinking about using pulse density modulation on hard switching converter, which is a novelty. And before, it doesn't make much sense because increasing the switching frequency is the side effect of pulse density modulation. And as you increase the switching frequency, of course, you reduce the efficiency of the overall system. But now, with wide bandgap devices, this could actually be a good time to start using pulse density modulation in our switching inverters. So our goal is to increase power density of power converters to eliminating the large common mode chokes that are typically used to meet the military standard, and also the bypass capacitor, either eliminate them or at least reduce them drastically. So not to be even close to the limits of the maximum bypass capacitance can be put on a ship. So as I mentioned earlier, modeling is the key. Here showing some example, this modeling for common mode has been published in the past. This is an example of a state space model that we did for the 4-leg inverter in the grid forming topology. So with the configuration for military standard 461 with LISN on the two input wires on the DC side, and modeling, of course, all the filters on the output, differential mode and common mode filters. And we chose to use for common mode analysis lamp capacitors. In particular, this is a capacitor and a resistant to ground. We had a lamp capacitance resistance from the neutral to ground and also from the midpoint of DC bus to ground. This is because our target is the switching frequency common mode EMI. And if you want to model to include the higher frequency EMI, like at the top limit of C102, so in the hundreds of kilohertz of the megahertz, then you're going to have to add more parasitic capacitance throughout the circuit. Okay, so and this has been widely investigated. So you can find many papers where they put capacitance between the heat sinks of the devices and ground or elsewhere in the circuit. By choosing to put only two capacitors, so one in the midpoint of DC bus and one at the neutral point, we account for common mode. But we don't account for the very high frequency common mode. And I will show you this later, but it is within the scope of what we're trying to do in this project. So it suits our need. Modeling should suit their needs, as I often mention to my students in class. You don't want to spend hours and hours running simulation if you don't really need to. So state space model for this system, I'm not going to go into details. Of course, you can find it in the paper. And here I'm showing the picture for military standard 461G general setup, so you can see the equipment under test, the ground plane, which is the copper plane, and the two LISNs. And here I'm showing the circuit for the LISN, which is a passive network. The line impedance stabilization network has the goal of decoupling any noise that can come from the power source, so that when you measure EMI, you only measure the EMI of the equipment under test. And so we have to account for the LISN. So the state space model includes also the DC side with the LISN, and so more state space equations. Again, this is not something that I want to focus on, but you can find those equations in some of the papers in the reference section. So with this, I want to now focus on some common mode voltage elimination strategies that we have been investigating in the last few years. So I mentioned pulse density modulation. So our idea is a 4-leg inverter with pulse density modulation to cancel common mode voltage. Pulse density modulation with respect to pulse width modulation has the advantage that you can switch all 4 inverter legs at the same time. So I will talk also about how we prototype for the experimental validation, and I will talk about the application of pulse density modulation on a 4-leg converter in grid forming configuration, as well as grid following configuration as interface to distributed energy resources. And this can be for shipboard or aerospace application, as well as also microgrids. And I will also talk about the application to motor drives of this idea. So first, I want to mention quickly how we did low-cost wrapping prototyping using MATLAB Simulink HDL coder to produce Verilog script and Vivado software from Xilinx FPGA to program the FPGA, and then do control hardware in the loop to verify that the controller is sound and works before switching to the actual laboratory prototype. And this is low cost because nowadays, of course, we are familiar with very expensive control hardware in the loop setups sold by several corporations. For this project, we were able to do everything with a Digilant FPGA development board shown in this picture. And in this block diagram, I show how we do it. So inside the FPGA yellow box, I have the control system that we're trying to prototype. And then I have the simulated inverter and the AC grid. The integrated logic analyzer within the FPGA allows us to get information out of the FPGA, such as what we get here on this picture, where we're showing, for example, the reference current with the actual current and the angle. And this interfaces with a computer for user interface. So when we do chill, so the first step, we send the gate signals to the simulated inverter, and the simulated inverter sends back information about voltage on the 3-phase and currents and back to the converter controller. Once we verify that this works with chill, and we gather pictures like this that tells us that the system the control system indeed is behaving as we expect, then we can switch to the last step, which is prototyping in the laboratory. So we have a hardware laboratory prototype, and so the gate signal gets switched from going into the simulated inverter to going into the hardware prototype. And similarly, instead of receiving the voltages and currents from the simulated inverter, we receive them from the 7 ADD converters that we have in the lab. So this allows us to do quick prototyping and also inexpensive prototyping. So let's talk about first the grid forming converter. So the architecture is the same as I shown in the previous slide, DC input and AC output with load that can be balanced or unbalanced. The 4 legs, as I mentioned before, are controlled so that you have always 2 switches on the top and 2 switches on the bottom at any given time. So the output voltage, the common voltage, is the sum of the 4 voltage is 0. And then we also, of course, have listen for this topology on the DC side. The control system for the grid forming inverter is an open loop sigma delta modulation that I'm showing here. So you take the error, you compare it to the assumed voltage, which is the voltage you expect by looking at the inverter gate drive signals and multiply by VD over 2, and then doing the integration here, sample and all, to create error on phase 1. A similar structure is not shown here, is done for phases 2, 3, and 4. And then these errors go to the switch selection algorithm, which makes sure that we always select 2 switches high and 2 low at any given time. And I'm showing here the ranking algorithm that we created for this structure. And to explain this, look at the left hand side here. These are the errors. For example, one part simulated errors for the 4 different phases. And you can see that for example, you have the error on phase 1 and 2 I. So those ones are going to be the 2 phases that we're going to switch I, which means the top switch is going to be turned on, while the bottom switches of the other phases are going to be turned on, and so forth. As you can see here, we always have 2 high and 2 low for each phase, and it's the ranking algorithm that figures this out. Of course, you have some small errors, and everybody working on common mode knows that sometimes there is a penalty to pay for differential modes. You can see, for example, here, you see that in the end, phase 2 really would like to switch low, but we don't let it because we have to have too high and too low at any given time. So it is important that we, in the lab, we verify also the differential mode performance of this converter because of the compromise we make. So going to the experimental setup for this system, we built it with 1200 volt silicon carbide Infineon MOSFET, and using type 1 power, so 200 volts RMS line to line, and a converter of 10 amps rating for selection of the C101 and C102 relaxation limits. And this is the structure. So what I said, no common mode choke, in reality, when we go in the lab, and because we are not modeling for the very high frequency EMI, we needed to put some small clip-on chokes. So these are tenths of the order of magnitude much smaller than a typical common mode choke. So let me show what I'm talking about here. So this is the setup. We use two Infineon 3-phase motor drive boards, and we took 2 legs from each one of them. And here is our control board. So in lieu of a large common mode choke, we had some small clip-on common mode and differential mode chokes. And these two are the least on this side. So first we verified that the THD was within the limit specified in military standard 1399. Okay, so the limit is 3%. Our THD was 2%, so this meets the limit. And we are happy with the result. So we are able to cancel virtually the common mode, but still meet the limits in the 1399. And here we see the time domain and frequency domain pictures for this. Then let's go to the conducted EMI measurements. The C101 limit is met actually without any of those chokes that I was showing. You don't need bypass capacitor, and you don't need any, not even the clip-on chokes for this. There is a large 360 Hz harmonic because we use a diode rectifier to produce a DC bus. So that's something that, of course, can be improved by using a different DC power supply. And the LISN does not suppress this low frequency, so it's still there. But these are the harmonics that we're really working with this new strategy of using 4 legs and pulse density modulation. That's where we really see the advantage of meeting easily C101 limit without any help. On the C102 is harder because, like I mentioned before, we chose to model EMI at lower frequency, but we didn't account for the high frequency effects. So we had to. That's where we had to add those common mode chokes and differential mode chokes. Let me show you what I mean. If you don't put those clip-on chokes, we exceed the limits. But see, it's not here the lower frequency, only the very high frequency. And this is due, of course, to the layout of the circuit. We didn't try to minimize this. This was not really within the scope of our project. But then we try to apply common mode chokes, and this is the result. So telling it most of this high frequency noise is common mode. And this one at the end is actually differential mode. If we don't put the common mode chokes and we only put the differential mode chokes, this is the result. So we get to experiment for the frequency EMI. This can be, of course, improved in the future modeling effort. But one thing that we want to look at also is the switching events. So we're dealing with silicon carbide devices, and they switch fast. So there is some ringing, and this can account from some of the EMI. But also, the simultaneous transition does not happen all the time. This happens when there is current in 2 diodes or 2 transistors. But if, due to the blanking time, and see this is the blanking time shown in this picture, the current goes in 1 transistor and in 1 diode for the 2 legs here we're seeing, then the common mode voltage, which is this black line, see in this chart's black line is the common mode voltage, basically pops up. And this is at the 200 kilohertz switching frequency that we're using for pulse density modulation here. So that's not good. But it's something that we probably can address by doing some blanking time compensation. And this is potentially future work. But also you can also have simultaneous transition if the current is in 2 diodes and in 2 transistors. So in this case, the common mode remains pretty much 0. Of course, this account for the high frequency EMI that we saw. So next, I want to talk about how we accomplish this common mode cancellation on inverters that are grid following. So these are converters connected to the grid. They can interface PVs or other distributed energy resources, as shown here. On chipboard, of course, you would have battery system, for example. And in this case, we have 4 leads for the experimental setup because our source is 4-phase AC. And so we have the equipment under test connected like this. We can do 2 different control strategies for the current control of this grid following converter. And one is delta modulation, the other one is model predictive control. And I will briefly show these now in the next few minutes. And we also came up with a novel switching selection algorithm for MPC to optimize the use of the FPGA. So delta modulation is shown here. It's simply just finding the error of the current and then going to the switch selection algorithm, which is shown here. And so that the 2 switches are high and 2 switches are low at any given time. This is similar to what I showed for the grid forming converter. And then model predictive control has got a little bit more complexity, but in the end, it's just a few simple equations to create the reference voltages from the reference currents and the measure currents that we see here, reference current and measure current, and then going from the ABC to the alpha, beta, gamma to go in the 3D space for model predictive control. What we're doing new here is that we actually have only algorithms that require simple equations and lookup tables so that we can actually identify the location of the reference voltage with just 1 single clock cycle on the FPGA. And that's pretty powerful because it simplifies many things. We don't need to use the arctangent function that requires more computation. So here for the grid following, I chose to show you some simulations to compare the 2 methods that I propose. So the 4-leg converter with pulse density modulation, delta modulation, or model predictive control. And we wanted to compare to the benchmark, which is 3D space vector modulation with a 2 millihenry common mode choke. So this is not an algorithm that cancels common mode, so you need to put a common mode choke in order to be able to meet the military standards limit. And these 2, delta modulation and model predictive control, virtually behave the same. And this is for C102, the higher frequency range. Again, as you can see, there is no emissions predicted by our models at high frequency. And I explained that, right? Because we are not actually modeling for high frequency. That is something that we may be able to do in the future if it makes sense. But for now, we wanted to focus on this frequency range. And so again, 3D space vector modulation with a 2 millihenry common mode choke barely meets the C102 limits. As we expect. And here, no common mode chokes in simulations. And we also wanted to make sure that the differential mode performance is not degrade substantially. And even though 3D space vector modulation does have a better THD, the THD is not much larger for delta modulation and model predictive control. The noise in the spectrum is spread more here, and of course, we don't have the switching frequency components that we had on 3D space vector modulation. And these are some time domain simulated waveform. Let's go to the experimental setup, where we, this time we chose to use actually the grid forming converter to create our grid. Because it turns out the power in our laboratory contains large 5th and 7th harmonics, which are really not pretty to look at. So we were able to produce cleaner power with our grid forming converter with the strategy I showed you earlier. And so we decided to go with this 4 leads in the setup. And then this is the equipment under test for this Sorry, I was going the other way around. Sorry. This is the laboratory power supply, the grid forming converter, and this is the equipment under test on the left-hand side, where we had to add a clip-on Kalmo choke and a small bypass capacitor as well. Again, this is the high frequency EMI, which we are not modeling, and of course pop up in the lab. Laboratory setup, we are still using two Infineon boards. In this case, we stacked them up. This is a different converter than the other one. We're using them at the same time. 4 listens here, and the Kalmo choke, as you can see, it's a clip-on tiny Kalmo choke used to suppress the very high frequency, as you can see on this zoom in picture compared to a pencil. And so the conducted EMI measurements are shown on these pictures. Here we have C101. For this one, you don't need a clip-on choke, so we are able to meet it without that. And the C102 limits was a little tougher to meet, and that's where for this high frequency, we are in the megahertz range. So this is 1 megahertz, this is 10 megahertz, where we were not meeting the limits without that small clip-on choke. This is due to the imperfect switching event that I was showing earlier on the other converter. So this is probably something that we can work on with some blanking time compensation, which should be really fun to do. So then our partners at Baylor University, my good friend, Professor Annette von Juan, she reproduced this entire grid forming converter in her laboratory, and using GaN devices, in this case instead of silicon carbide, and using also a Typhoon control system. So let's see their test bed. This is test bed. So being able to repeat the same experiment in 2 different laboratories across the country, I think it is important to be able to see that, this strategy really works and is not only dependent of some custom hardware we put together in the lab. So they use Typhoon HIL 402 and again with the FPGA, and they are implemented sigma delta modulation. The setup is identical to the one we had. It's shown here in this picture, but their load was a motor. So specifically, we wanted to test a motor load. So these are the experimental measurements for a 230 volts, 5 horsepower motor, a 50% load. And these are the time domain waveforms provided by Professor von Juan at Baylor. And these are the conducted EMI without Kalmo choke, where they measure C101. Again, here the 360 Hertz harmonic due to the diode rectifier. C102 limits met really easily on the at the higher frequency. So being able to apply to different type of setups and different type of loads is really important. So I want to conclude now talking about the future work as well. So physics-based models are important, and of course they can be tuned depending on what you're trying to model. Then 3-phase inverters with a 4th leg and pulse density modulation produce theoretically 0 Kalmo voltage. And the Kalmo elimination methods that we presented were all experimentally validated on inverters built with wide bandgap devices. And even though the high frequency EMI was not entirely eliminated, I'm talking about the EMI between in the megahertz range or the high 100 kilohertz, but they were easily suppressed with clip-on chokes. So future, I mentioned some of these. We could look at the high frequency EMI modeling to fine tune some of those small chokes we put in, and we can do this with potentially some collaborations, and also blanking time compensation. But it's important too for high power application on shipboards and aerospace application to be able to expand it beyond the 2-level inverters. So can we do this on multi-level inverters? That's a research question that we would like to answer in the near future. I'd like to acknowledge the sponsor, the Office of Naval Research, Captain Lynn Peterson, and my collaborators, Dr. Alex Julian, and then my students, Lieutenant Matt Storm, graduating this quarter with distinction and with a bunch of awards. Lieutenant Foster graduated in June, is somewhere on a submarine right now, and the new student is a U.S. Marine Corps Captain Rob Tubbs, who is coming up to speed and working on these future research ideas. And I want to thank the collaborators at Baylor University, Professor Von Juan, Agamo, and Yokochi, and their student that implemented the motor drive application of the idea. These are the references for those of you who would like to know more about the ideas I presented today. The papers have more details. And I want to thank you for attending, for your attention. And if there are any questions, I'll be happy to answer. And I want to thank you, the sponsors for today's webinar, IEEE, PELS, and IAS.
Thank you, Giovanna, for a wonderful talk. I'm sure the audience will concur that this has been a very insightful talk. We do have quite a few very good questions, so we'll get right into the Q&A session. So the first question is, could you talk about the sizing or design guide for AC side EMI filter? And why don't you consider a DC side EMI filter?
Okay, so DC side filter. So let's go back to maybe one of these pictures here. So DC side filter was not, yeah, we just put a differential mode filter at the output of the inverter, and that was sufficient to, with then the addition of a small count of chops to meet the military standard. So you may be able to do, actually in a previous version, when we did the very first experimental validation, we did put some filtering on the DC side as well. So you can do that too. Yeah, you can do DC side filter, or on the other side, of course, of the LISN. Yeah, that's what we chose to do. It's an interesting question, probably worth investigating. If there is a reason to move the filter from the AC side to the DC side, then yeah.
Okay, all right, thank you for that. So then the next question is, do you see any major differences between grid forming and grid following inverters in terms of potential EMI issues?
Actually not. We don't see very much difference between the two as far as meeting the military standard limits. So yeah, most of the noise we were struggling to with, as I mentioned, is a very high frequency due to the layout. So yeah, we didn't try to make a perfect layout. We just put together the converters in the lab. Our goal was to really prove that the lower frequency here, the C101 and the lower frequency 102. So no, we didn't investigate anymore. That's a good idea for future work.
Okay, all right. Thank you for answering that. Could you talk on how to estimate the common mode winding ground motor capacitance experimentally or with FEM simulation tools?
So the grounding capacitance between the load and ground, right? So you're talking about probably, yeah, you're talking about this one, right? The
right.
CNG. Okay. So there are papers on this topic, okay? And in the 90s, we did one. For example, we did an entire experimental measurements on a motor, and we measure really all the parasitic components. Well, we measure basically the frequency response of the motor, and then we plotted it with using lamp parameters. So that's one way. But there are other papers that have been written even recently on this topic, on how to make experimental measurements to come up with the frequency response. So you take a load, you apply some different frequency voltages, and then you look at the frequency response, you plot, and then you try to match with some body plots with the lamp parameter. That's one way. But I know there is other more sophisticated ways in literature that people have done this. So I invite whoever asked the question to do a thorough literature search. There is lots that was done on this topic.
Okay, thank you. So the next question is the EMI test setup used in accordance with the EMI limits, that is the C101 and C102? If not, then does comparing results with the standard limit make sense?
Yes, we did set up. Yeah, that's a good question. It's not exactly. We had limited space in the lab, but we probably don't have exactly 2 meters. And so, but yes, does it make sense? Yes, even if it's not a perfect setup, we are not, we're an academic institution. We're not certified to qualify equipment for going on a ship, right? So it is not our job. This whole project was a proof of concept. So we wanted to make sure this was sound, that we could that will work. And then if when you go to the perfect setup in the end and you go for qualify your equipment, you end up with slightly more high frequency EMI, then it's gonna be easy to take care of with clip-on shocks or some other means of this type. So yeah, it is a very good question, and I don't claim that this is the perfect setup exactly per meter standard. We didn't measure and we didn't do all the things perfectly, but we are satisfied as a proof of concept. And next, in order to put this idea on a ship, we're gonna have to start doing a much more than what we did for validation.
Sure.
Thank you.
Yeah.
Thank you. A very good question.
Yeah. Okay. So the next question is, you mentioned that the common mode voltage perturbations were observed during the blanking period of your inverter. Can you explain the mechanism by which these voltage spikes occurred?
Right. So we had one of the yes. So I want to show you the switch. These are the key pictures really for this. See, I have the common mode voltage here measured in black. These are measure results, okay, on the silicon carbide Infineon MOSFETs in the lab. So you can see here that we're switching always too high and too low, right? As I was showing in this picture here. So we have 2 switches high. Pulse density modulation allows for the synchronization of the switching of the 4 legs. So at any given time, I have too high and too low. So then if you go back here, so not always, not all legs switch at 200 kilohertz every time they're allowed to, but they could. So like in this case, for example, all 4 legs switching at the same time. When there is simultaneous transitions, then the common mode is really not there. It's almost 0, except for really this ringing due to the ringing of the device, the silicon carbide devices. And probably this effect can be improved. We didn't try to improve any of these, but this is what I was talking about earlier, the 100 kilohertz, 200 kilohertz tones, the multiple basically of the pulse density modulation frequency result in non-zero common mode voltage. When there is the blanking time, well, the blanking time is everywhere, right? But in this case, I have current going in one transistor for one leg and one diode in the other leg.
Yeah.
I hope that makes sense, because yeah, if the current is in 2 diodes or in 2 transistors, then you have simultaneous transition here, see? But if you have in this case, that's when you have the common mode spiking up.
Right. Okay. Thank you. So there are a couple of questions about the added 4th leg, which I'll combine. So does the added 4th leg require same current as the other 3, or can it be a lower current rated? That's
a very good question. In fact, this was pointed out by my friend, Professor von Juan, last time we met. Yeah, if the load is balanced, then you don't need to have the 4th leg rated as the other 3 legs. So for a motor drive, for example, you can retrofit. You can retrofit an existing 3-phase motor drive with a lower rated 4th leg. Okay. And that's one idea actually that Professor von Juan had last time we discussed, and she was going to probably go and try in her lab. Okay. All right. Thank you. So another question is, can you comment on if the conducted emission, solving the conducted emission problem, would that help solving a radiated emission too? And is there any interdependency between these 2 types? Typically, they are connected in the sense that if you have a high frequency conducted emission on a ground wire, for example, on a wire, then if the wire is long enough or is placed in the wrong place, that can cause radiated emission. So yes, in general, yes. Now, specific case, there are also other forms of radiated emissions, not just the ones produced by the current flowing on conductors. So, but for those, for sure, yes.
Okay. So the next question is on the pulse density modulation. So firstly, is the switching losses by the PDM, how do they compare with the traditional ones?
Yes, so that's a good question. That's something that we haven't gone and done yet. We presume that we've done only some theoretical calculations. So we in theoretical calculation, the losses with the silicon carbide devices are comparable to the losses with the regular silicon devices on a pulse width modulated converter. But more investigation is needed. But we think that it is this got really potential for overall having the same efficiency. So comparing apples to apples, comparing basically a three-phase inverter with the PWM and silicon devices with the three-phase four-leg converter with the PDM and the silicon carbide or GaN devices. We think that we should be able to reach the same efficiency, but that is something that for future research, hopefully, some future collaborations.
Okay. So the follow-up question on the PDM is the PDM done with hard switching? And if so, would the simultaneous turn-off of multiple legs increase turn-off transient voltage spike?
Yes, it's done on hard switching. Yes, and the pictures on the screen right now, those are the experimental measurements for switching with PDM, silicon carbide devices. I'm not sure if this answer completed the question.
Yeah, I think the other part of the question was so would the simultaneous turn-off of multiple legs would that increase the turn-off transient voltage spike across the turned-off devices?
And you can see it here. Yeah, I'm not sure. Yeah, that's something that I'm not sure about. That all you can see here is all we looked at. So here, for example, we have 4 legs switching at the same time, and yeah, I mean, if this maybe a little bit higher ripple compared to the ripple on the previous slide, it's not really. It looks equivalent to me, but I'm not an expert. Yeah, I'm not an expert in devices, so this is not exactly my expertise. But it's a very good question and something for definitely to look into.
Right. Okay. So the next question is: have you compared the estimated EMI versus real measurement to check the accuracy? How was the RBW filter bandwidth for the measurement?
Say it again. How was it the bandwidth?
How was the RBW filter bandwidth for the EMI measurement? Or how does the estimated EMI compare with the real measurement?
Oh, okay. Sorry. Yeah. Yes. So estimated EMI. It's we have them actually. I don't have them for the grid forming converter. They are in the papers, but they are here for the grid following application. So yes. So as I mentioned earlier, so the lower frequency C101. Sorry, no. This is I'm looking at this side. The lower frequency C101 is comparable in the model, but C102. We are not predicting those high frequency noise that we saw in the lab, and I explained that why, because we're only modeling for lower frequency common mode by using lamp parameters at the let's go back here, lamp parameters at the load and at the midpoint of DC bus, right? So we're not, if we were to add all the capacitance to ground between each device and ground, or maybe distributed in the winding, or maybe distributed in the transmission line. I mean, there is lots of papers on more detailed modeling. Then we'll probably be seeing more of the high frequency EMI, but it was not within our goal to account for the high frequency EMI. In fact, you can see here in the lab, in the lab without any filtering C102. This is where all the noise is that we are not accounting for.
Right. Okay.
Thank you.
Yeah, thank you for that. So the next question is, can this scheme be extrapolated to higher power levels like 100 kilowatts to 1000 kilowatts? And how large would the common mode choke be for such systems?
Yes, that's a good question. That's what we will need to do, keep working towards. Yes, for probably people with enough experience on high frequency EMI could probably guess from what we're seeing here. But yeah, that's future work, the activity that hopefully we'll get to do maybe with some collaborations.
Right. Okay. All right. Thank you. We are already past 12, but there are about 3 or 4 questions, so I'll just quickly go through those. So how important is it to incorporate an accurate model for the electronic switches in the developed model?
So to model for the switching of the devices.
Right. Yes.
Okay, so yeah, we're not, yes, thank you for the question. In our model, we're considering these ideal switches. And that's, again, these affects the high frequency noise that we were not counting on in the simulations, right? So yeah, the higher frequency that we don't see, particularly the spike. Let me show you actually that there is a really good picture here. See, this one is due to the non-ideal switching of the device that we're not modeling. So yeah, that can be done by a more accurate model of the devices.
Okay. All right. Yeah.
Good point.
So the next question is related to the 3D SVM. So is the comparison between the 3D SVM and MPC delta done on simulated 4-leg inverter or in the experimental setup?
No, we only did it in simulation. So yeah, good question. No, we didn't set up a 4-leg converter with 3D space vector modulation in the lab. So no, we don't have a direct comparison. This does not, I mean, this 3D space vector modulation is the classic one, right? The one, there was a paper from Virginia Tech from 2002, I believe, right? That is cited in all of our papers. So it does not, they're not trying to cancel common mode here. A few later papers did try to also do in 3D space vector modulation, maybe some common mode cancellation, but we're just using the standard. So there is no attempt to cancel the common mode here. And so you need a large common mode choke. That's why also our LISN are rated for low power. So that's why we haven't even attempted to do 3D space vector modulation without common mode choke.
Okay, yeah, thank you. Okay, we'll take one last question. So would you comment on the overall cost of the inverter and efficiency using the defined setup?
Yes, so that's exactly the perfect question to ask in order to go from laboratory validation in an academic environment to product. And that's what we're hoping to get some partners and collaborators to move this project forward, to prove that really indeed is a good idea to go and put in a ship or aerospace. You need to move to the next stage, which is doing more accurate measurements and full power measurements, like somebody also was asking. And I think there is very good potential. So I think what we proved with these proof of concept papers and the work in the lab is that there is very good potential that this is really applicable. But until you actually build the converters and you measure the efficiency or do more accurate analysis, you won't know for sure. So we're thinking there is good potential, but this is exactly the perfect question that we need to start answering in the next stage of this research.
All right, yeah, thank you for that. I think we are already over time, so and we've answered almost all the questions. And thank you, Giovanna, for addressing all the questions. We had a lot of good questions, and you took time to answer each of those. Thank you for that, and thank you for the wonderful presentation.
Thank you, everybody, for the questions. They're all excellent questions. Thank you.
Right. I'd like to take a couple of minutes just to thank our co-sponsors, the IAS Education Department and the Santa Clara Valley PES IAS chapter. We've had a lot of wonderful co-sponsors throughout this year for helping us with all the different events. And we look forward to bringing forth more events to all the attendees going forward in the next year. As I mentioned earlier, we would also be having in-person events. So if you're in the Bay Area, please be on the lookout. You can follow us on our website and also on eGrid for more events. Thank you, everyone. Have a nice day and happy holidays to you.
Thank you, Kishan.
Thank you.